First of all, welcome to my presentation. It is my pleasure to present to you today our research on battery SOC and parameter estimation using multi-rate moving horizon estimator. So before we dive into technical details, let us take a moment to share a story behind our collaboration. So I'm Tushar, a PhD candidate at UDelp, and I've been working on battery modeling, while Federico is a PhD candidate at University of Rome, and he has been working on moving horizon estimator. So last year we met in Toulouse, France for one of the EECI course for PhDs. While having a coffee conversation, we realized the potential of MHE in battery modeling. Together, we have embarked on a research endeavor, and this is that particular joint work that I am presenting here at IFAC. In this presentation, I'll cover battery modeling, moving horizon estimation, adaptive MHE, and two different variants of MHE named multi-rate and parallel, and finally conclude my talk with future direction. Starting with battery modeling. While many of you are already familiar with battery modeling concept, I'm not going into technical details of equivalent circuit model or ECM, as our emphasis lies in the application of multi-rate moving horizon estimator for real-time battery state of charge and parameter estimation. But just one point on selection of first order ECM, that we wanted to strike a balance between accuracy and computational efficiency, which allow us to achieve reliable estimation without compromising real-time capabilities. Indeed, in battery systems, parameters often exhibit nonlinear and time-varying dependencies on state of charge, temperature, and health. This complexity poses challenges for accurate parameter estimation and require robust modeling techniques. In our initial work, we have taken non-calculated guess that the parameter dependency on SOC is polynomial, out of which SOC OCV has higher order polynomial dependency, and it is known through offline experiments, while other parameters have lower order polynomial dependency on SOC, and we try to estimate them through moving horizon estimation. So to address the challenge of parameter estimation in battery systems, various solutions exist, particularly Kalman-based filters, which are lightweight and widely used in estimation problems. However, they are not inherently robust and often rely on linearization of system dynamics. On the other hand, moving horizon estimation offers robustness in handling nonlinear systems. However, the computational burden associated with MHE poses a challenge, particularly in real-time applications. Our research aims to address these challenges by providing tuning methods for the standard MHE. Additionally, we propose MHE variants specifically designed to reduce the computational burden. This will make real-time battery state of charge and parameter estimation more practicable and accessible. So now let's discuss the moving horizon estimator in more details, specifically focusing on general nonlinear system and concept of n-lifted system. So n-lifted system, namely the procedure through which a continuous system is described by a discrete one with a finite number of samples. Consider the parameter set theta and n-long measurement buffer y. The n-lifted system, denoted by h, is a system that incorporates the initial estimate psi 0 theta 0 and uses state transition map to reach from past to current time step. The MHE problem aims to minimize a cost function j in which the first term represents the output mismatch between the measured output yk and estimated output hk, while the second term, arrival cost, consists of the estimated values at the beginning of the optimization process of psi 0 theta 0 and the current. So as mentioned in the work of Kang, the measurement buffer length n must be higher than dimension of psi and dimension of theta to get the local convergence of the estimation. This definitely increases the cost, and now we are looking for a solution through adaptive moving horizon estimator. So through initial experiments, we realize at least third order polynomial relation is essential to describe battery parameter dependency on SOC. In the work by Shen, an adaptive approach is employed to estimate only the initial coefficient alpha 0 of parameters using the MHE framework. This selective estimation is carried out due to two main reasons. First, computational burden, and second, numerical instabilities. So in our proposed solution, we introduce a technique to reduce the computational burden. We adopt the signal variability index proposed by Oliva and Carnevale in their previous work. The signal variability index, denoted by delta y, is a measure of variability in the new upcoming signal compared to the signals which are already there in the buffer. So for all our experiments, we utilize the Simulink-based parameterized ECM test bench as the data source to get the ground truth, especially on parameters. To discharge the battery, we used modified hybrid pulse power characterization current signal. Moreover, the measurement signal has been affected by Gaussian noise with zero mean and standard deviation of 5%. So figure shows a signal richness index delta y over the whole output trajectory, considering different downsampling values NTS while keeping measurement buffer length n is equal to 30. NTS is equal to 20 provide maximum signal richness in this particular case, and that's why we have chosen that one for our future experiments. So these are the results of parameter estimation we got through adaptive MHE, where n is equal to 30 and downsampling factor NTS is equal to 20. The optimization happens on all the polynomial parameters as well as states SOC and voltage across RC pair V1. Here R0 and R1 are definitely following the trend while estimation of C1 is quite accurate. So computational cost of MHE increases with buffer length n and downsampling factor NTS as the estimated states needs to be propagated till the current time step. So considering n is equal to 30 and NTS is equal to 20, adaptive MHE takes 4.5 seconds for single iteration, while standard MHE with NTS is equal to 1 takes 0.28 seconds for single iteration. So by definitely using larger NTS, the MHE tracks slowly changing variables, for example parameters, quite well. But we also want to track fast dynamics. So we want to keep the performance in the parameter estimation while reducing the computational cost and tracking the fast dynamic. And that's why we are proposing multi-rate and parallel moving horizon estimator. So in case of multi-rate moving horizon estimator, we have dual sampled measurements. So sample 1 to 5 with no downsampling to capture the fast dynamics, while sample 6 to 30 with downsampling factor 20 to capture the slowly varying state of charge dynamics. These multi-rate moving horizon estimator definitely help us to improve on SOC estimation, but poses another challenge. Because now we only have 1 second to do computation, because new measurement signal is coming at each second compared to 20 seconds of time lag which we had with adaptive MHE. To solve that, we propose parallel MHE, where slow-paced MHE is used to do the model parameter estimation, while the fast one is used for state of charge estimation. Indeed, the most significant improvement lies in the computational burden, which drops significantly for fast MHE, as you can see from the table. Thus, the parallel MHE with multi-rate slow MHE can be implemented online, justifying its uses against normal multi-rate MHE we saw earlier. So results in terms of SOC estimation are presented in the figure, where standard, multi-rate and parallel MHE are compared. Indeed, the parallel MHE slightly worsens the performance with respect to multi-rate one, but improves with respect to standard. Parallel MHE has to wait until multi-rate buffer is filled, and hence there is a spike at t is equal to 480 seconds around. Yeah. As far as the parameters are concerned, the parallel MHE estimation follows the trend presented in multi-rate one. Now moving to conclusion. So the MHE is definitely a valuable tool for SOC and parameter estimation. However, its performance is influenced by choice of buffer length n and downsampling factor NTS. And to address this challenge, we exploited the signal variability index from Federico and Carnevale's work to tune the downsampling factor, allowing us to strike a balance between computational burden and estimation accuracy. Additionally, we introduced multi-rate MHE, which considers different timescale dynamics, and also parallel MHE, which enable real-time implementation by solving the multi-timescale dynamic issue. For future work, it is important to investigate process noise and its impact on estimation accuracy. Furthermore, exploring the model parameters, dependency on temperature, and aging will provide valuable insight for improving battery modeling and estimation technique. Thank you for your attention. We have covered main aspect of battery modeling and use of MHE for real-time state and parameter estimation.